Have you ever really stopped to think about what happens after you swallow a pill? I mean, it feels like magic, but it's actually this complex, fascinating, and believe it or not, a really high-stakes journey through your body. Okay, let's dive into this.
Right? Think about it. You've got a throbbing headache, you take this tiny little pill, and somehow it knows exactly where to go and what to do to make the pain stop. Well, today, we're going to follow that pill on its incredible mission.
And look, this isn't just a fun little thought experiment. As this quote makes really clear, understanding this journey is absolutely critical for using medicine safely and effectively. This is the very foundation of a huge field of science called pharmacology.
To make sense of our pills adventure, we first need to get familiar with the two fundamental rule books that govern literally everything that's about to happen.
It's really a two-way street. On one side, you have pharmacokinetics. Just think of this as the story of the journey itself, how your body takes in the drug, moves it around, and eventually gets rid of it. Then, on the other side, you've got pharmacodynamics. This is the mission, what the drug actually does to your body to make a change. You need both to get the full picture.
So, let's start at the beginning with that first rulebook, pharmacokinetics. How does our pill get into the system and start traveling to where it needs to be?
This whole journey can be broken down into 4 distinct stages. And lucky for us, scientists packaged it into a really easy-to-remember acronym, ADME. That stands for absorption, distribution, metabolism, and excretion. This is the drug's entire life cycle. Let's tackle the first 2.
First up is absorption. After you swallow that pill, it's pretty much useless until it can get into your body's main transportation superhighway, the bloodstream. This is the drug's first big hurdle, just getting into the system.
But for any drug you take by mouth, there's a huge challenge right at the starting line. It's called the first pass effect. Before a drug can get into your main circulation, it has to take a detour through the liver. And the liver acts like a security checkpoint, immediately breaking down and deactivating a chunk of that drug. It's why the dose you take is always carefully calculated to make up for this initial loss.
Okay, so once the surviving drug molecules make it into the bloodstream, stage 2 begins, distribution. Your circulatory system is like this massive network of highways, and the drug is now a passenger, cruising throughout the entire body to reach its target.
But here's a super cool detail. Not all the molecules travel the same way. Some of them grab onto proteins in the blood, kind of like hailing a taxi. Now, while they're bound to that protein, they're inactive. They're just along for the ride. It's the unbound or free-floating molecules that can actually hop off the highway, get into the body's tissues, and do the real work.
And some destinations have incredibly tight security. The blood-brain barrier is basically the ultimate bouncer for your central nervous system. It's this super selective wall that stops most things from getting into your brain. Only very specific types of drugs are designed to get past this bouncer, which is why treating conditions in the brain can be so darn tricky.
Okay, so our drug has been absorbed and distributed. It's arrived at its destination. Now for the really exciting part, pharmacodynamics. What does the drug do now? How does it actually complete its mission?
The whole secret comes down to these things called receptors. All over your body, your cells have these tiny little structures that work just like locks. And a drug is designed to be a very specific key that has an attraction or an affinity to fit perfectly into one particular lock.
And there are basically 2 main types of keys. First, you have an agonist. This is a key that not only fits the lock, but turns it. It activates the cell and causes something to happen, like a pain reliever blocking a pain signal. Then you have an antagonist. This key fits in the lock, but it doesn't turn. It just sits there, physically blocking any other keys from getting in and stopping a reaction from happening. Both are incredibly useful in medicine.
So, if we're thinking about drugs as keys, how do we compare them? What makes one drug stronger or, better than another one? Well, it turns out pharmacologists look at 2 really important measurements.
The first one is potency. This is all about how much. So looking at this chart, drug A is way more potent than drug B because you need a much smaller dose of it to get the exact same effect. It's just more powerful milligram for milligram.
But, and this is a big but, more potent isn't always what you need. The other measure is efficacy, and this is all about the maximum possible effect a drug can have. So here, drug A has a much higher efficacy because no matter how much of drug B you take, it will never ever produce as strong a response as drug A can. So remember, potency is about the dose, efficacy is about the total effect.
All right, Mission accomplished. The drug has done its job. But it can't just hang around in the body forever. The body needs a cleanup crew. And that brings us to the final leg of our journey, metabolism and excretion.
Let's go back to our ADME roadmap for a second. We've covered A and D. Now it's time for M and E. Metabolism is the process of breaking the drug down, and excretion is, well, getting it out of the body. A really key concept here is a drug's half-life. It sounds technical, but it's simple. It's just the time it takes for your body to get rid of half the drug in your system. A drug with a short half-life gets eliminated fast, so you might need to take it more often. One with a long half-life sticks around for a while.
So, the drug gets broken down, mostly by the liver again, into byproducts. How do those leftovers actually get out? Well, while tiny amounts can leave through your sweat or even your breath, the body's main exit route is through the kidneys. They filter all that waste out of your blood and get rid of it in your urine.
So there we have it. We've seen the whole journey: absorption, distribution, metabolism, and excretion. And when you see this whole complex process laid out, it becomes really obvious why medicine isn't a one-size-fits-all solution.
I mean, every single person's body is a little different. Things like your age, your body weight, your genetics, and especially how healthy your liver and kidneys are, all of these can dramatically change how you process a drug. Even the time of day you take it can make a difference. This is exactly why your doctor has to consider all these things to figure out the perfect dose just for you.
So from a simple swallow to an incredibly complex dance of chemistry and biology, that is the amazing journey of a pill. It really makes you wonder, doesn't it? As we get better and better at understanding all these little individual differences, are we heading for a future where every single prescription is perfectly tailored not just to a disease, but to the unique person taking it?